Thank you very much for joining us today in this colloquium. It's a pleasure to introduce you to Dr. Gaspard Duchêne. So he did his PhD around 2000 on protoplanetary disks and binary stars. And he was supervised by François Ménard, who's a long-term collaborator of mine. That's why we met first and we came in contact. Then he went to UCLA in Los Angeles in 2004. And there he was working actually more or less similar to what he was doing before, but then had some papers about the galactic center. And then he went back to Grenoble, which is in France, and started a postdoc there. Before, he had the opportunity to go to Berkeley, and there he spent most of his scientific career, so between 2007 and 2023, working on debris disks. Do we have? No. We have Elke Lothringer here, but she is working on debris disks. So yeah, there he came in touch with debris disks. So these are the kind of second generation dust disks, which are more optically thin, doing some imaging, modeling of them. And so for a long time, he was using a tool that's called MCFOS, which we also use sometimes. This is a Monte Carlo radial transfer package where you can do very precise continuum modeling of disks, etc. But then finally, in 2023, he came back, and now he's working again in Grenoble with François Ménard. So back to the roots. And this now is a little bit connected to a new ERC. So there's an advanced grant called Dust to Planets. And they are looking for really collecting really the best observations we can possibly do for disks with ALMA, better models. I mentioned MCFOS, and also better laboratory data about the growth of dust and aggregates. Okay, let's over to you.
All right. Thank you, Peter. Can you guys hear me now with the mic? All good. Well, it's a great pleasure to be here and to meet already some of you, and of course to see Peter again after seeing each other. Today, what I want to do is actually go over a number of studies that have come out of a collaboration between François Ménard and Carl Stapelfeld, which started a few years before my PhD. And for over 25 years now, we've been looking at disks, protoplanetary disks, with a special angle when they're edge on. So you'll see that image again later. You'll see why we care about these disks. And I will say the one thing I'm proud in this project is how, not so much how many results we've obtained along the way, but how we've convinced the community that these edge on disks are actually cool and not just some oddity that is kind of fun, but who cares really. So hopefully I'll convince you of that by the end of the talk. All right, so to get the things going, let's step back and think about the big picture. The question is about how we form planets. We know there's thousands of planets of all sorts of huge diversity of planets in the around other stars, and we want to know how they form. So we know this comes hand in hand with the formation of the stars themselves. So a molecular cloud collapses under gravity, forms a star. Angular momentum puts some of the gas and dust into a disk, and somehow in that disk, planets form. And we want to understand how easy it is to do and how that connects to the properties of the planets at the end. Now, in the most commonly admitted accepted process, we think of planet formation as a bottom-up process. We start with very small dust grains. We somehow glue them together until they get to be larger and larger solid body things that eventually could even capture gas and form giant planets, or just stuck at the level of a terrestrial planet or an asteroid or a comet or something like that. There are many questions associated with that process about timescales, about where it can happen, what can happen to break it down. We think there are many barriers that we don't really understand how to break them, and yet nature knows how to break them. So we have to figure out how that works. And those are the kind of like general questions we're interested in answering as a community, and in particular, as Peter explained, within that ERC project that François is leading. One of the key questions we're interested in is the interaction between the dust particles and the gas in that disk. Most of the mass is in the gas, but the dust particles are the ones that form the seeds for the planet. So we need to see how they interact. And there's a long study of all the processes, there's a long list of processes that have been understood at least at the basic level for a long time, but then we're trying to probe them quantitatively in protoplanetary disks. They're summarized in a fraction of a figure from Leonardo Testi's review in 2016. I'm not going to read through all of them. Maybe the more important one for this talk that I will talk about is related to the drag force that the dust particles feel when they travel through the gas. The gas is not in Keplerian orbit, it's slightly sub-Keplerian because of gas pressure. And the dust particles would like to travel at Keplerian orbits, but then they feel a drag, and therefore that slows them down, they lose angular momentum, they move around. What is expected to happen is that they will settle vertically to the midplane, and then they will migrate inwards towards the star. So that's illustrated in this simulation. That's just one model. There's many out there, but I'll pick this one. In each of these panels, the dark blue dots represent gas particle. This is an hydrodynamic simulation with the two fluids. One is gas and one is a dust particle of one size at a time. And the cyan particle represents the small dust grains. In the four panels, what is changed is formally in the paper, it's the Stokes parameter, but it's related to the grain size. So I approximated that with the grain size, although there's complications hidden behind it. And what you see is that the different grain sizes don't behave the same way at all. At the top, the very small grains are fairly well coupled to the gas. They are spread up vertically the same way as the gas and radially as well. That's because they're so small that they're completely entrained by the gas. They don't move relative to the gas, so they do whatever the gas is doing. At the very bottom, meter-sized bodies and even larger, they decouple completely from the gas. They're so big that their surface is not enough to feel the drag compared to their mass, their inertia, and therefore they keep going on their Keplerian orbits. They don't care about the gas. In the middle, when something happens, that's the sweet spot where the particles are big enough to feel that drag force and yet not decouple from the gas. They settle and they migrate inwards. That's the kind of stuff we would like to measure. The models make predictions for how efficient those processes are. And it seems that they're maybe even too efficient compared to what we observe. If we believe the models, we would think that 10 centimeter size particles all settle and migrate to the star in like a few thousand years. And then there would be no dust left in your disk. And obviously we wouldn't be here if that was the case. So there is more physics we need to understand. That's the kind of background to what we're doing. Now, how do we probe that? Well, we need to see the dust. That's easy. There's multiple ways of doing that. I'll focus on the two extremes for now. First of all, you can take your favorite and state-of-the-art adaptive optics system on a large telescope. Here we're using the VLT sphere instrument on one particular star. The star will be right in the center here. It's hidden behind the mask, so it doesn't blind you because it's extremely much brighter than the disk itself. And then you can see the disk surface here and here. And if you've never seen an image like that, you're not sure you're seeing the surfaces quite well. So I'm going to point out where the upper and the bottom surface are. Maybe that helps. And that's not enough, then I'll put something you might know next to it. That's what you're seeing. The star is right in the center here, and all the light you're seeing is at the very surface over here and the bottom side over here. But what's in the middle here in the disk would be the denser, most opaque regions where no light gets to, and therefore that cannot scatter to you. And that's why you have what we call the midplane. That's darker in the center here. That's the thickest, most opaque region. No light from the star gets to that point. Okay, so hopefully that helps. Because these observations are typically taken in the optical or near infrared, you're basically sensing micron-sized dust, so pretty small, sort of interstellar-like, or maybe a little bit larger, depending on who you talk to, but pretty small. Obviously, before we get from micron size to planet size, there's a lot of range. So the next thing we do, at least chronologically, I guess, we go to ALMA and we take images in the continuum, like around a millimeter. So we're probing millimeter-sized dust now. In the same disk, it's the exact same object, not to scale it, because this is a lot larger than this. I couldn't put it to scale properly. Shows something quite a bit different. It doesn't look like a top and a bottom surface, and that's because it's actually very thin. What you're seeing here is the millimeter dust that has settled to the midplane, and you're seeing sort of a pancake. It's brighter in the center, it's a bit hotter. If you squint enough, you might see some sort of a spiral, which is kind of exciting. Who is that spiral? I won't talk about that. But the point is that we have good tools to probe where and how distributed really the dust is as a function of its size. We can compare the micron size, the millimeter size, and hopefully connect that back to the settling models I was talking about before. Okay. So we can do this exquisitely for a few objects when you get great data like this, but a handful of objects doesn't make a full picture of what bad formation looks like. What we need is go towards much larger scales, and I'll use the demographics word again here, where the good thing is not only can we do these kind of observations with specific, very hand-picked objects that might be very biased, but we can actually do it with objects, with large variety of objects. And ALMA provides galleries of objects in one particular star-forming region. In this case, it's torus. And you see all sorts of structures and even sizes of disks. That's when we start looking at the ensemble of all the disks around young stars. Because when we look at the exoplanet, the thousands of exoplanets we know, they're around randomly picked stars, not just one particular one. We don't know whether those stars had a particularly large or massive disk or anything like that. We just know there's a planet there, or multiple planets. So we need to see the ensemble of all the disks, either with ALMA, so we probe the millimeter dust, or with sphere, and we probe the micron-sized dust. And this is again torus, but seen with sphere. So there's a lot of data available. That's great. Now we need to put it together into a comprehensive picture of what's the connection and how are these disks connected to each other, and can we see evolution evidence, for instance. Okay, so that brings me to sort of where we are in the talk. I went over sort of the general planet formation context very briefly, tell you what we're going to talk about. And I'm going to present you how we approached it for, like I said, 25 years from a different angle, literally. And then hopefully I'll go over these 4 topics of kind of results coming out of these studies. And I'm not sure how well it's going to fit in the time, but Peter will keep me on track with that. So if I have to skip a little fast on some of them, you can ask me questions afterwards. So for the younger in the room, you might know an object called HL tau from this image. Very famous, the first time ALMA imaged a protoplanetary disk with great resolution, and all of a sudden it was a revolution, there's rings everywhere, there's planets everywhere, all that stuff. The picture in the background is actually an HST image. It's the first image taken with HST back in 1990 of a young star. You're like, well, let's look at a young star and find planets around or disks around this young star. It's going to be great. And HL tau is that messy stuff out there. Booming bright, so you detect it very well. But it's crowded into its own envelope, remnant envelope. It's a borderline class 1 object, so there's still stuff around, and you cannot see through to the star. It's just opaque. So you don't see the disk. Of course, ALMA showed us that the choice of HL tau was really a good one, but it just didn't know it 25 years before that. However, in that same picture, if you squint enough, you'll see that little guy down there. It's called HH30. And if I zoom in, it looks like that. There's a sort of a black thing over here, another one over there. There's a jet popping up perpendicular to it. And what you're looking at here is a protoplanetary disk, but you're looking at it exactly edge-on. Meaning the disk, which is opaque, is blocking your view to the star, so you cannot see the star. The star is somewhere in the center here, but you just can't see it. And you're only seeing scattered light off the surface of the disk. And it works because you have 90 degrees. Okay, so that was a bit of an oddity, but that was actually the first, I believe, the first paper on the protoplanetary disk with HST. That's a 1996 paper, so it goes way back. And then the first models trying to explain that with some Radial transfer tools to say, well, let's assume a certain structure for the disk and see if we can replicate the image. But it felt like an oddity at the time, like it's a weird thing. It's a cool thing because from a practical point of view, you don't have a star in the middle. So you don't have to worry about being blinded by a booming bright star in the center of the disk. Like I said, for the sphere image I showed you, we have to push the star behind the mask and block it so we don't get blinded in the observations. And if you do that, you're also blocking part of the disk. And if you're interested in that, you just can't see it. And it makes for more complicated observations. You need to deal with the fact there's a super bright thing, you're looking for a faint thing, you need to integrate a long time, but you have to do short exposures. It's a mess. When you have an edge on disk like that, you don't care because there's no bright thing. So that's great. The other thing is, because of the geometry, now the z-axis, the vertical axis, is directly seen here. You can tell how far up the disk goes. It stops right about here and right about here. So you can measure the vertical structure to some degree. It's a little bit model dependent, but you can measure almost directly the vertical structure of the disks. And so if you're interested in settling, that's great. That's what you want. If you take the same disk and you tilt it over 45 degrees or something, projection effects make it such it's much, much harder to infer that. So it's not perfect for everything, especially on the radial direction, because the disk is optically thick, but still it can be useful. So, of course, not all disks are edge-on. You cannot choose. You cannot move your disk around and make it become edge-on when you want to. You have to be lucky. It's a little bit like transit of exoplanets. You have to have the planets in the right plane. Otherwise, it doesn't transit, and there's nothing you can do about it. But we wanted to understand after a while, we started thinking about, we found a few. We're lucky. It's cool. We have a bunch. I'll show you some pictures later. But what can we do with that? What does it say about the distribution of these properties? And for that, we needed to understand when, under what circumstances, does a disk become edge-on? Meaning, when does it block your view of the star? That's all we care, right? That's our definition of edge-on disk. It just says you cannot see the star straight through. And so we considered a bunch of models, battery of models, depending on different properties, and I'll get back to that a bit later. But to give you a sense, these are synthetic HST images. So you take a relative transfer model, you convolve it with an HST PSF, and you just tilt it by different inclinations. And this is the spectral energy distribution of the same system. And in the images, so this is clearly edge-on. This is still kind of edge-on. I can see the two sides, that too. And there, maybe I see something, I'm not sure. And here I just see the PSF of HST. So what I would call an edge-on disk in this case is anything at 81 degrees and above. But that number depends on the specifics of the disk. If it's larger, smaller, more massive, less massive, it'll be different. What comes along with that edge-on disk image is a change in the shape of the SCD. At low inclination, the SCD is dominated by the star at short wavelength in the optical and the infrared. And then there's infrared excess from the disk itself. But it's more like a shoulder in the SCD. By the time you get to be edge-on, the SCD turns out to be two humps like this. Two bumps of roughly equal height. Depends on the details, but roughly equal height. So if we find objects with SCD look like this, then we can go and point HST, and hopefully it will look like that. And we'll find a whole lot of new edge-on disks. And that's basically what we did over the years. Carl Stapelfeld was the leader on that part. And here is a gallery of some of the disks we had identified in one sample of, I want to say it was 23 targets, and we had like 11 or 12 edge-on disks in that. So we were very effective at finding the right candidates so we can get the most out of HST out of it. I'm not going to walk you through all these disks. You can see there's all sorts of diversity. There's some in binaries, some big, some small ones. But the point is now we have enough that we can start to look for trends and the collection of it, the ensemble of it, rather than studying one object at a time and figuring out what it means, the more bigger picture. So now, for many years, what we've been doing was using HST and AO and KEC or VLT to image objects, and they look like this again, those two sort of parallel nebulae. And I'll focus on these two objects. You don't have to remember the phone numbers, but you recognize them because I'll show them over and over again. We've done a lot on these two. And then we moved on to ALMA. So we were looking at the millimeter grains now, and they look like this. This one is this one, this one is this one. And it's great, but there's a big gap in wavelengths between KEC or VLT and ALMA on the other hand. Meaning we know what the micron size dust does, we know what the millimeter size dust does, but we'd like to know what the intermediate size dust does, the 10 micron, the 100 micron. So for that, we need observation at wavelengths that are intermediate. And part of what I'll show you today are new results coming out of James Webb, which does exactly that. It covers the wavelength range in between. Not fully, but at least part of it. So I'll leave the question mark for now, and then I'll show you some results later on. Okay. So moving on towards the results. So there's a lot of stuff here. We'll see how well we do that, but I'll start with this first part here, talking about the ensemble view, sort of demographics precisely. So, like I said, we wanted to know which disks are actually edge-on. As I showed you from that one example before, it's a matter of inclination, but the specifics depend on the model, on what kind of disk you put in there. So we constructed a broad grid of models. And there we've varied as much as we could within what the observers, us, also see in disks in general, in terms of the distribution of size of disk, the distribution of mass of disk, and so on and so forth. And we were trying to figure out what are the biases in our method to find new edge-on disk. We're pretty good at finding new ones, which is great, but presumably we're biased in some ways that force us to find certain disks and not others. So we need to understand which ones are we missing, so then we can put the whole thing in context with the ensemble of exoplanets out there. So we try to put the dependencies that observers do find, especially as far as stellar mass goes. The disk properties often depend on the stellar mass. I'll pass you the detail, but we try to take that into account best we could. And we started doing a big grid and computing probabilities and things like that. You don't have to read any of the axes, because that's way too small and way too many. The point is, guess what? The higher the inclination, the more likely you are to be edge-on. Like the closer to 90, the more likely it is that the disk is opaque. Not a big discovery right there. If you have a higher mass disk, it's also going to be more opaque because the opacity is proportional to the mass. So no big surprise there. But at least we recover stuff we expected, so that's reassuring. We also found that if you had a thicker disk, meaning a disk with vertical aspect ratio, which is characterized by a gas scale height, the thicker that disk is, the more it's optically thick. At least the more likely it is to be optically thick at random angles, because it has a larger so you can put it this way and that way, and it's still optically thick. Whereas the thin disk, well, you'll have to be just right there to be optically thick. So again, not a big surprise, but we can quantify that. And the bottom line is, as we drew our numbers, is that we expect that somewhere around 6 to 8% of all the stars that have a protoplanetary disk in a given star-forming region should be edge-on by our definition, assuming they're randomly oriented in the sky. And it turns out we don't know that many, not yet. Even in the regions with most studies, we're still missing some. So there's still some question mark as to whether that means there are some that we have not found yet, or whether the way we've constructed our grid and our dependencies is not quite right. So that's open for interpretation. But we're trying to get our way towards understanding our biases.
What is the percentage that is observed?
The percentage that's observed in the region where it's the most studies is probably around 4%. It's not way off. But in other regions, for reasons we don't quite know, it's more like 1 or 2%. And we think the reason for that is undersampled SEDs, actually, where we don't quite understand the SEDs well enough. We're talking with some of you this morning about crowding and how it's hard to measure fluxes at long wavelengths. Spitzer has a resolution that was just not good, for instance, and that limits the ability to construct good SEDs. But it's almost certain that in some regions, like Ophiuchus or Lupus chameleon in particular, that there are more edge-on disks we just haven't found just yet. And many of these disks are pretty small. So if they're too small, then we cannot really find them unless we use HST. Like even good seeing ground-based data won't resolve them. So to try to understand that, we did more recently a new survey that was again targeted based on SEDs, but in just 4 different star-forming regions, trying to be as complete as we could. And now this time, we only have our success rate, which was 50% the first time around, was more like 10% now. So it looks like we're starting to scrap the bottom of the barrel. We're not finding as many more as we thought. The interpretation is still open for debate. We still find the nice good ones. You probably can see because of the light. This one has little weird things popping out on the sides. I have no idea what that is. We can talk about that if someone has an idea later on. But we're still trying to understand whether the question is, are we targeting the wrong sources? Are we using the wrong or incomplete SEDs? Are we just not having the right representation of the population of disks? Who knows, right? There's a lot of interpretation possible, and we're working on that. Carl Starhoff is actually going to be on sabbatical in Grenoble for a few months, started on Friday. No, it's starting tomorrow. They're arriving tomorrow. So hopefully we'll talk about that a lot. So hopefully you'll know more about it in a few months. But one thing that did come out of these surveys is what I call here a curious dichotomy, meaning there's 2 populations of disks, and we don't quite understand what they are. The first population is what I would call the textbook disks. That's the HH30 I showed you before. That's another couple. They look exactly like you would expect them out of the models. They are pretty thick vertically. They extend pretty high up compared to their radius. You can sort of see the flaring, although the curvature you see in the images is not quite directly the flaring of the disk, but it's kind of connected to it. And they look exactly what you'd expect. Fine. However, others look a lot different. They're a lot thinner vertically compared to their radius. Maybe it doesn't show up too well again because of the contrast, but the aspect ratio is much smaller in these guys than it is in these guys. They also seem to have a much sharper and vertical, the extreme in the vertical directions are much sharper transition towards no light whatsoever. And they're a lot flatter. They're a lot less curved like this. They're a lot more like straight lines. And we don't quite know what that is. But what we do know from our grid of models is that these guys should be rare because they're thin vertically. They should be less frequent to be seen edge-on if they're randomly oriented. And I'm not going to quote a fraction because I'm not sure yet we have stabilized that. It's not 50% of the disks look like this in our sample, but it's certainly more than a third. So it is a significant fraction, and that's despite the bias. So that's not an oddity. That's not a one-off. There's a weird guy somewhere, which we thought at the beginning when we had 1 or 2. One of the interpretation was, well, hold on, maybe that's an evolution thing. That's exciting. Maybe the normal one, they're just like normal ones. There's gas and there's dust. But maybe the other guys here, they're already very settled. And even the small grains have started to decouple and settle towards the midpoint. So they're kind of like more evolved. So maybe that's the answer. The way to address that was to look at where the gas was, because what we see here is small dust. And if it's settled, it should be separate from the gas. The gas should be thicker than the small dust is. And if you overplot on top of these images where the CO is, and so in these images, I apologize, I should have made the figure the other way around. The blue is the CO, and the contours are the scattered light. So the contours match the image here. And the blue that's behind is the gas. And you can tell that this is thick in scattered light, but the CO goes all the way up to out here, if not a little more here. So dust is thick, gas is thick. Over here, dust is thin, gas is thin. So even the gas is thin as far as we can tell. And if you want a gas disk thin, you need to make it cool. That's the only way that it won't puff up. And if you try to play a game for this particular object, what we inferred from the scale height or the total height of the disk that we see is a temperature in the midplane that's more than half, or less than half, sorry, than what we expected it to be, given what we thought of the star and just propagating the light somewhere and saying at 100 AU, the temperature should be, say, 15K or something. And if it was 15K, it would be 1.5 times thicker in the gas than it actually is. So it clearly is cooler. The gas is cooler in these thinner disks. And the question is, how is it cooler? How does it work? Because the light illumination is always going to be there. And it looks like maybe some shielding, of the light is needed to cool it down, to prevent it from heating someone. We don't quite know what the answer is, but there clearly is these two families of thick and thin disks that need to be interpreted. Okay, how we do? Okay, not too bad. All right. So as I mentioned, the original reason we got into this edge on this game was because we wanted to look at the vertical structure. So let me go into a little bit more detail about the vertical structure, and we'll say a little bit about the radial structure along the way. So again, the game here is to compare what we see in scattered light, how thick the disk is, that's the micron size dust. Then we observe the same disk with ALMA, we're probing the millimeter dust, and we are hoping to find it a lot thinner, right? So in 2020, Marion Villeneuve, a former graduate student of François Ménard, conducted a survey of a dozen or so edge-on disks, even though one of these at least is really not edge-on, as you can see from the image here. But basically what we were saying is, they're pretty thin vertically compared to how extended they are radially. If you remember the images I showed you before, that aspect ratio is definitely a lot thinner. In fact, it was so thin that for the most part, we couldn't resolve the vertical direction of those disks. So they were not thicker than X, but it wasn't quite a measurement because it wasn't high enough resolution. So we went back on a couple of these at higher resolution later on to try to improve on that. One of them being this guy over here, although we also have higher resolution image of HH30. And again, here I'm comparing now the ALMA continuum, very thin pancake. It's this guy over here, shows up here. And that's the scattered light image from HST. So you can really tell the difference in vertical direction here. Much, much thinner. Okay. As we go to even higher resolution with ALMA, because you can use the longer baselines of the array, you start to detect the disk and to actually be able to say something about the vertical direction. It may not be obvious from where you stand, but the way the profile looks like along the vertical direction here, it's not because of the beam, it's actually we're resolving it. We start to measure the thickness of that layer that's emitting in the millimeter. In this other guy, and again, it's the same two sort of flagship objects I've been using since the beginning. In this case over here, you might probably see that there is like an outer ring over here, then a bit of a gap, and then another ring a little bit inside here. You squint enough from a distance, hopefully it looks like that. This system is about 87 degrees inclined. For you to be able to see that there's a gap here with something outside and something inside, it means that wherever there is this emitting dust, must be very, very thin vertically, because otherwise, if it was a little bit thick, projection effect would completely hide the gap from you. So we can use that to constrain the actual height of the millimeter emitting dust. So either we resolve it directly like this case, or we see substructures like these. And when you do that, what you find are total height, the full vertical extent at 100 AU of the disk is no more than 5 AU. That's a total height. If you think about it as scale height, assuming some sort of Gaussian profile or something, that means probably 1 or 2 AU, maybe half an AU. So aspect ratios of 100 to 1 between the vertical and the radial direction. Whereas for the gas, as Peter could tell you, this is more like 10 to 1. So clearly the pebble layer, what I call the pebble is the millimeter emitting dust, is something like 10 times thinner than the gas disks. And that we see, in fact, this is a flared thick disk. This is a thin flat disk. In both cases, we have the same thing, that the millimeter is a lot thinner. And we see that in both of the families that I was talking about earlier. Okay, so what about intermediate grains? I'm going to get to James Webb finally. A while back when I was at UCLA, as a matter of fact, I was at Tech with a student doing some binary study, and I told her, you should look at HK tau, because I like it as an edge on disk in it. She was not interested in the edge on disk, she was doing something else, but she still observed it. And what we got is an image like this. So you have a binary star, you have a bright, booming bright star over here, that's the primary star, and then there's a little smudge over here. And it doesn't look like much, but I cannot tell you how excited I was when we got that image. I remember coming back from the restroom and looking at the screen from the distance and squinting at like, there's a disk. And that's the edge on disk. It's in fact just the right way. It's so cool. So we knew there was an edge on this from HST, and it's aligned exactly like this. And we're seeing scattered light at 10 micron off of the edge on singular. Meaning, even though a 10 micron disk emits all the light, we're still opaque, and we still see scattered light out of it. Now, doing anything more than just saying, oh, it looks like we detected it and it's somewhat extended is hard on an image like that. So from the ground, that's probably the best you could do at the time, and not much better these days. But of course, if you go to JWST, it's a lot better. So this is an image not of the same system. And now we have images, in this case, up to 4 micron only. I'll show you the longer wavelengths in a second. And now you can see the nice bipolar structure, the midplane in the middle. It's a 3-color rendition. You can see it's bluer over here and orange here over there. I'll get back to that later in the talk. Gorgeous image. Oh, by the way, there's a galaxy out there. That's fun. There's galaxies everywhere in JWST. But this is, again, only up to 4 microns. It's not a fair comparison to the image on the left. But if I show you the images made of the 8, 13, and 21 micron, still looks a lot more convincing that there's 2 parallel things with a midplane in the middle than this image over there. So with JWST, at least on the largest disk of this, so we can actually get images all the way to 20 micron and still see the vertical structure of the disk. And therefore, we can play the game and ask, oh, is the disk getting a lot thinner as we go to longer wavelengths, as we would expect from settling, or not? So to show you what that looks like, here are again these JWST images. Actually, this is an HST optical image. And these are JWST images up to 20 micron over here. I think it's 2 and 4 micron, if I recall correctly. We'll see in a couple of seconds. And that's the ALMA continuum image from that same object. So we do see, if you look at it, the distance between the two areas here goes down with wavelength. This is thinner than this. Okay? So the disk appears to get thinner as a function of wavelength. Now, there are 2 effects that can explain that. One is settling. If you take the dust and physically make it small, less extended vertically because it's larger and settles, then it will look like that. But also, with pretty much any dust population out there, the longer wavelengths you go, the more the dust is less opaque. The less the dust is opaque, I should say. So therefore, the opacity goes down, and therefore the 2 surfaces, if you just reduce the opacity, the surfaces will get closer to each other. To the point where if it was becoming optically thin, then you wouldn't see that anymore. You would just see a single lane over here. So the question is this decline that we observe here due to just opacity, or is it due to settling? So we start by looking at what we call the standard model. And the standard model meant all the dust grains are fully mixed at every single size everywhere in the disk. Completely extreme. And what we saw was that it can decline a little bit from the optical to 20 micron, much as the same way as the observation, so not too far anyway. But then, of course, by the time you get to ALMA wavelengths, it doesn't work anymore because the millimeter dust here is just too distributed vertically. So we knew we had to put some settling at some point. So rather than trying to think about physical models of settling, we went for something more simple, a pure parametric to try to guess what was going on. Basically, what we said is all the grains from the smallest up to a critical size are fully mixed with the gas. And above that size, they get settled increasingly strongly as they get to be larger and larger. And basically, our parameter is what is that critical size? What is the maximum grain size that is fully mixed with the gas? And we did that. We tried a few models. And here are the cases where that critical size is either 1 micron or 10 micron. And basically, 10 micron is the right answer for this particular disk. It goes down in terms of thickness, but not too much. If this one gets too thin, and yet it already produces a pretty thin submillimeter map. Doesn't match perfectly, that wasn't the point, but it does have the right tendency to explain those observations. So the bottom line is, in this particular disk, grains up to 10 microns are not settled, and the larger ones get to be settled faster and faster as you go to larger sizes. How do 10 micron grains stay all the way up to the surface is up for debate. It's not so easy. If they were hard compact spheres, they would settle some because they would be just too massive. And so you have to find ways to make them less massive. One way could be to make them aggregates, fluffy stuff, porous stuff. That's just an option. It's not necessarily the answer, but that's the kind of things we're trying to think about. Now in the radial direction, here is an overlay again of the ALMA map in red with the HST image in black. You can see already that the millimeter dust doesn't go quite as far out as the micron size dust, probably because of migration, although there could be other physics involved. If you compare now the extent of the continuum to that of the gas, That's the gas as far out as it goes in one velocity channel. I won't bore you with the detail of ALMA data cubes, but there is gas all the way to a radius of about 900 AU, hence the scale on the left. And if I flip back and forth between the continuum and the gas, you can see that the continuum stops right about here, and the gas goes much further out. Okay, we knew that already. All disks that people have looked at with high resolution in gas and dust, the gas goes further out by a factor of 3 or 4, something like that. Not a big surprise. Question is, where there is gas, is there small dust? Because if the small dust is fully mixed everywhere, it could be even in these outer regions. And I don't know if you remember, when I showed you, it's the same old disk I showed you a few slides ago, there's a galaxy next to it. The galaxy actually sits right about here, if I put it in transparency. It's closer to the star than the extent of the disk, meaning the disk is that thick radially, and the galaxy is sitting behind that disk. And you see the galaxy through the disk. Let me tell you, there's not much dust out there, because it doesn't take much dust to block the light of a galaxy. So there is stuff out all the way out to here, but you can see a galaxy through it. We can also see the dust in absorption in what we call silhouette, but it doesn't go further out than the scattered light, so probably about here. So that region out here seems to have very, very little dust. What does it mean? I don't know. I'm pretty sure it's not completely dust-free, but it has to be at least pretty dust-poor. And what that means, whether it's an evolution process, whether it's something else, is up for debate. So as far as this cycle 1 survey went on, because that was one of the first cycles on James Webb, we did observe 3 other objects. I won't show you all the details. We had some interesting, weird things happening. Some of them, there's some possibility of warps here and there. There are other, that image has done the rounds the last few weeks. You might have seen it already. That's HH30, the same prototypical, the very first one, but now seen with James Webb in multi-wavelength. Gorgeous image. I could say a lot about it, but I will skip over it. And we're currently in the process of analyzing a cycle 2 program where we observed another 13 edge-on disks, because people got excited about the first one, so they gave us some more time. Thank you, TAG. These ones were a bit smaller, mostly in size, so we didn't observe them all the way to the same long wavelength because the resolution of James Webb is just not enough at 20 micron to do all of these guys. We're working on the observations yet, on the analysis, so I won't show you more from that program just yet. Okay, let's see. Perfect.
So now you're about at 40.
Yeah, that's great. I have 2 more topics to tell you about. Hopefully that will be just perfect in terms of time. So, as I said, we went to this edge-on disk because we thought about the vertical direction. That's what we're most interested in, and that's what we've focused a lot of analysis, especially in these first papers. But as we've done that, we started looking at more of different things that we could do in these observations. So that just jumped at us, and we had to do something about it we didn't know what to do with. So surprises. As usual, you observe an object with a new system, you find some weird stuff. So here's one thing, for instance. This is again the same Tau 4121 disk, this large one, the one with the galaxy next to it. And this is an image with HST at 0.8 micron, and this is an image with James Webb at 2 micron. And the resolution is almost the same. If you think in your head lambda over d, James Webb is 3 times larger, the wavelength is 3 times larger, it cancels off, right? So one thing that I hope you can see is that in both the nebulae, the vertical direction is a lot more extended. There's a tail of stuff over here that is just not here. And yet the James Webb image is by far the deeper. If there was something, you would see it in James Webb. You can tell there's noise in this, and you cannot even see the noise in this rendition over here because it's a lot lower. So there is something that produces light over here and over here at 0.8 micron that doesn't show up at 2 micron. What is that? So one thing we've been thinking about is, well, what if there was some small dust, sub-micron size, that had been lifted up above the disk surface, and then because it's small enough, it can scatter optical light pretty well, but it doesn't scatter at 2 micron because small grains just don't scatter 2 micron light. They don't interact with one another. So we're currently working with Kathy Clark in using some of their photoevaporative wind models, although really what we need is just a description of where the dust is. We don't really care about how the physics of the launching of the wind is not necessarily what we care about. All we need is there's gas flowing out, and that gas can entrain small dust. And of course, it will entrain very small dust pretty well, but it will not entrain the larger grains because they're too massive. They will not go away. And so the question is, can we reproduce things like these using a model like this and putting in some small dust and trying things? So we are at the level of toy model for the moment. Working on a paper trying to put that together. But here is one model for this particular object. Again, we're going to flip back and forth, observation, model, and the main bulk of the disk looks a lot the same, but here I've put some small dust and you can see it scatters, but it doesn't scatter at 2 micron. So qualitatively, these observations could be indication of small dust being entrained in winds from the disk surface. And the morphology of how the light is distributed over here probably says something about where that wind is launched. Is it close to the star? Is it over the entire structure of the disk? And my hunch at this point is that it's the latter. It's launched over tens, if not hundreds of AU. It's a really large disk for that matter. So 100 AU, 200 AU, something like that, not just like a linear 1 AU or something. Okay. That same system also has another weird thing, and on the left here is the image I have on my title slide. I'm not sure you'll be able to see it again, but this is a 3-color rendition from James Webb, and I don't know if you can see in red, there's sort of a cross here. Hopefully you can. That cross, which at first I thought was just an instrumental artifact, actually is not. It is astrophysical. We could have ruled out every single artifact we know of, and it shows up at 7 micron and 13 micron. Like, what the hell is that? And here is a high-pass filter image of that 7 micron. You can see that X over here. That shows up very cleanly. This is the disk surface over here, and this other thing is right there. What we think is that it's some sort of a cone that is limb brightened. And that has probably something to do with the wind, because it's way up above the disk surface, so it cannot be the disk itself. And when we wrote the paper, we sort of like threw out there as a possibility, because we didn't know any better, that it was either some H2 emission, because there are some strong H2 emission lines in those filters. Okay, why not? Some sort of a flow traced by molecular hydrogen is pretty typical. Or it could be PAHs, very small nano carbon-rich grains that get excited from UV photons out of equilibrium. I'll get back to that idea in a minute. Keep that in mind. But we didn't know any better, and the reason we didn't know any better is because all of our program is designed on imaging with broadband filters. So we have no spectroscopic information other than it's somewhere in that wavelength range, but we cannot tell you what wavelengths exactly the feature is at. So we cannot tell you if it's H2 or images. The other object that kept coming back and forth over since the beginning of my talk of 1631-31 are the flat guys. Here are the images from, again, HST and James Webb, and they look a lot the same. There's no evidence for a wind in this case. The morphology is very similar between the two images. But if I switch from these short wavelength images, this is 2 micron, to the longer wavelengths, James Webb, 7 micron, 12 micron, 7 micron, the image is up to scale. There's no change of scale. And all of a sudden, this does not look like an edge-on disk whatsoever. It looks like a big bright blob that's actually resolved. It's not a point. And then fuzzy stuff all the way around, like little wheels or something. What that is? No clue. But again, H2, PHs, who knows? Be my guest. We can talk if you have ideas. So PHs, going back to that. As I mentioned, this is something that's been known. Peter could say a lot about PHs. Probably maybe heard from him already on that topic. It's been known for a long, long time around her big stars, intermediate mass young stars, detected in spectra all over, very rarely detected in T-Tauri stars because they're not as UV rich. So the thought was, we don't know if this pH is grain, but there's not enough UV, so we never see them in spectrum. And then we started wondering, like, could it be that there is a little bit of PHs, but in the general case where you see the central region right away, straight up, it's not edge-on, you get overwhelmed by the light from the central source. And the little weak pH features just are not detected in the spectrum. But if you put the disk edge on and you block all the center, and the pH comes from further up, then you can see it. So François started working on a very simple model, toy model again, not fitting anything in particular, but you do a star with some UV excess, you make a regular kind of model for a disk. It's not pure triangles in the models, I swear. And you make a thicker one that you fill with pHs magically. We don't care about how much there is yet, we're not at that point yet. And then you ask the question, could it be that a simple T-Tauri star with a standard UV excess can excite those pHs? You can see them. And I apologize for the figure being not of the highest quality, but in these images, you see a continuum 2 micron image and then 2 images at 2 different pH features without and with some UV excess, with fractional UV excesses that are reasonable, that are plausible, let's say. And all of a sudden, between the continuum and the pH filters, you can see the booming bright pHs. So now we're working on trying to get the numbers right to see if it's something that we can compare properly to the observations. I don't have the answer to that yet. However, just about last week, the paper came out on Tau for 2021, the one with the X, remember, that showed some images specifically tailored for the pH bands and the H2 line emission lines. And that's at 3, 6, and 13 micron. And in each of these panels, green traces the H2 and red traces the pHs. And from those maps, as they constructed them at least, it looks like there is both of these things contributing to that X feature. How all that connects back to the physics of the winds and so on is something we need to think about moving forward. But clearly, we're onto something here. Even in an alpha solar mass kind of Titari star, we can get pH emission detected with James Webb and imaged, not just detected in a spectrum, but imaged. Okay, perfect. 4 more minutes to do the last point. So the last point takes us a little bit away from images, but takes us to spectroscopy, because one of the things that James Webb is going to be great at, well, there's many things that James Webb is going to be great at about protoplanetary disks. And Peter was just showing me this morning some spectra with a gazillion amount of lines, and amazingly, you find a model that actually matches them, which I find absolutely fascinating. But another topic that people have been interested in, especially for edge on disk, is the question of ices. The presence of ices in disks is telling us something about how they might grow, because the stickiness of ice and rocks is different, although there's big open questions out there about this. There's also the question of deposition of volatiles and water down to the terrestrial planet-forming region. So knowing where and how much ice there is relevant in the context of maybe even habitability down the road. And unsurprisingly, people are starting to use spectroscopy with James Webb to detect ice bands. And here are some images for edge on disks. So HH30, which you've seen already, Tau 421, the one with the X, and then HH48, another one. So what you see is around 3 micron, there's a big deep. It doesn't look like a very prominent here or here, but it's a log scale here. On a linear scale, it looks more like this. That's water ice, absorbing around 3 micron. At 4.2, 4.6, you get CO and CO2 bands. And so you can see that there are all these ices are present in those systems. It's not so surprising, because in scattered light, what you see is the outermost region, the one part that's in front of you. So you see the cold regions far from the central star, and when it's cold, all the elements just turn into ices. And therefore, you're not so surprised to find that there is absorption features from those bands. And that got us thinking a little bit about, obviously there's a huge community, I should say, before I say that, of people interpreting this kind of spectra to say something about the type of ice you're looking at, the size of the grains, whether there are other species involved, the detailed shape and location and wavelength of these features is saying something about their physics. So that's something we don't really do, but we know about. And I was curious about, in general, what people do is they take a spectrum and then they have laboratory spectra, absorption spectrum of ice or something, and just try to find the one that matches the best. And that got us thinking about whether that was the right approach. So work that's been done by a grad student in Grenoble, in Martignan, has been to look at how does it exactly work when you start to look at a disk edge on rather than face on. And it turns out that everything depends on the geometry. Where you are, how you're observing the object makes a big difference. So if you're looking at the system from kind of above, a low inclination, you're way up there, you have direct starlight from the star, no ice feature, it's just a star. And then you have some scattered light that can scatter on the disk surface and get to you. So you expect a little signature of scattered light. Some people try to do that in imaging with James Webb. You look at it edge on, now your direct line of sight is completely absorbed. So no light will get to the star to you at 3 micron. And all you're going to see is pure scattered light, like this. We expect a spectrum typical of scattering, not absorption. And then if you're in the middle, what we call the grazing angle geometry, you still have some scattering. You have a little bit of direct light, but that is also absorbed. Right? It's not completely transparent, it's a bit opaque. So you get a combination of absorption and scattering, and now you need to think about your spectrum as a combination of these two effects. And it turns out they don't have the same spectral shape. And as a result, depending on how you look at the system, the spectrum will look different. So we built a model, Lauren built a model with a uniform distribution of ice and dust. It's not mimicking any specific object. We could tailor it to anything else, but for now, we're just trying to do something very simple, same properties everywhere. And we just change the viewing geometry and where we measure the spectrum. Do we measure it in the brightest region or on the edge over here or in the bottom over there? And these are the spectra you get. On the edge, you always get the same spectrum. That's cool, at least it's consistent. But down in the central region, the spectrum changes a lot. It changes in how deep the spectral band is, the ice band is. It even changes in where it's centered, a little longer wavelengths, a little shorter wavelength. For the sake of time, I'll go a little fast on these figures, but we've measured the depth and the central wavelength and showed that it changes a lot. And it changes by enough that you could confuse what your interpretation is of the spectrum. It could confuse amorphous ice to crystalline ice, for instance. If you just look at what's the central wavelength of that band, can say something, can change something about how you interpret grain sizes and so on. So the bottom line is, even though you look at one single disk, it has the same properties everywhere, depending on how you are, when you look at it and how you look at it, you're going to get different answers. So you do need to take the full relative transfer into account with scattering and absorption to properly interpret those kind of spectra that are out there. Give that one. Oh, and that has to do, one last thing I should say. This effect actually comes from the fact that absorption and scattering don't have the exact same spectral properties. They have like troughs and peaks that are not quite lined up in wavelength. And depending on whether absorption and scattering dominates, it shifts things. And sometimes it does a funky thing. I should have pointed that out here. It has a little blue bump, something to the left of the main band. And that was kind of weird. First time we thought we had a relative transfer problem or something. Turns out we were convinced it's in the model. And then the week we were going, or the day before we submitted, or the day we submitted, I don't remember now, the paper came out on the archive with a disk that's exactly at grazing angle. These guys didn't know anything about our paper. And guess what? CO and CO2 have big booming blue bumps, right exactly what we're seeing. Maybe water, but it's more complicated with water because it's broader and everything. So clearly this is happening, and this is to be interpreted properly with a full relative transfer model. Okay, and I think I'm out of time, so I'm going to skip with my conclusions here. I hope convince you that this kind of edge on this are actually cool for a lot of reasons, and others I didn't have time for. I'm happy to take any question. Thank you.
Fascinating talk. I learned a lot. Are there any questions?
Thanks, Gaspard, for a nice talk. The question is your first point, dichotomy of disks.
Yeah.
You said that the fraction of thin disks is more than that's what's expected, yeah?
Yeah.
So what's the reason for that? I didn't understand.
I have no clue, because I don't even know where they exist in the first place. So I should rephrase. What we do know observationally is that there are comparable numbers of thin and thick. But we also know from our grid of models that we're biased against the thin ones. So the thin ones are at least as common as the thick ones. But if you ask anybody before, they will tell you all of this should look like that. And maybe there's one weird one that has a weird, I don't know, a warp or something, but that's going to be 1 in 10 or 1 in 100 or who knows, right? No, it's just as common as the regular kind of disks. Physically, clearly, those disks have to be cooler than we think they should be. We know roughly the luminosity and temperature of the central star, so we can sort of follow from relative transfer where the temperature should be with a regular structure. Something doesn't line up. So my best guess is that there's something in the inner regions of the disk, closer in. We do not see because it's edge on, that's casting shadows or something that's shielding the light from getting to these outer regions, and those outer regions get to be cooler than we think they should be. But I have no preconceived assumption as to why this should happen at all, let alone how often it should happen.
Maybe also questions from non-experts, like more like very general, maybe here, Ludmila?
You have inferred these winds that you basically need to, first of all, put out the small grain sizes, but also the pH. I find it weird because normally when you see the structures, you have very clearly more clarion. So why do you suddenly have vertical winds? Where is this coming from? And do you have any idea what mechanism is driving that?
That is a great question. I don't know either. Well, you talk to people doing both HD and MHD models of disks. They'll tell you it's not so hard to launch a wind out of the disks. Okay, I'll accept their word for that. And then the real question is, can you actually get dust that's in the disk originally to be lifted up to the base of that wind? And then it gets entrained with the gas, that's easy. It's that transfer region that's the difficult point. And I've read, I don't know many papers in the last few weeks about the efficiency of that process and how it depends on this and that. It's super dependent on which physics you think dominates. But typically what people will agree on is grains up to a fraction of a micron, a sizable fraction of a micron, let's say between 0.5 micron and 2 microns, let's call it that way, we'll get through that barrier and then we'll be able to be launched. pHs are just very, very small grains. So they're the easiest to carry along, right? So the question, however, is why do we not see evidence for winds in every single one of them if it's so easy to launch those winds? Because at the surface of this, we see dust. That's what we see. So we know there is dust.
Really look at pHs. So I had actually a remark. Can you go back to the slide where you discussed the thinness of the gas when the dust is thin?
Yeah.
Because I would exactly expect that behavior. The thing is that you are saying CO equals gas.
Yes.
And however, from the chemical models, yeah, maybe first find the slides.
No,
it's very clear.
It's a dichotomy thing. Yeah, sorry, I didn't go as long as I needed. Yeah. That's the one you're thinking about.
So that's the CO observations, right?
Correct. Yeah, background is
Yeah.
12 CO. Yeah.
The thing is, in the chemical models, the CO only lives as long as it is not facing the light. So you need the shielding of it dust to make the CO survive. So at some point when you go up, you lose the CO because of photodissociation.
Yeah.
And so for me, that's not at all
A surprise.
a surprise or a proof that these guys might not also have thicker
Correct.
gas, because gas is not equal to CO.
Correct.
PAHs is a different story because PAHs are super stable. You can't destroy them with UV.
Yeah.
So when you show me a PAH observation, then I
It's
believe.
going to be taken next month.
Okay.
However, I should rephrase because then I realize I maybe misstated my point here. When I'm saying the gas is too small, it's too cold here, we were not using the CO to infer that. We were using what the scattered light was telling us. We need basically we're inferring the scale height of the micron size dust, right? That gave us a scale height, which we turn into a temperature.
I see.
And for that disk, it turns out to be at 100 AU, 6.5 Kelvin. But in our redshift transfer model, if we put a star and at that 100 AU, we would get 15 Kelvin.
But physically,
It's not quite the same thing.
it should be a combination of the temperature, you're right, but then also the turbulence.
Absolutely, absolutely.
Anyway. Yes, Dirk?
I maybe have a very basic question. The light we see in some of the disks that is perpendicular to the plane of the disk. Where does this come
So
from?
the straight up.
Yeah, exactly.
So that's a jet. So part of those young stars are accrete from their parent disk, right? The material falls onto the star and keeps building it.
Yeah.
A fraction of that goes up along the polar direction into a pretty narrow atomic jet. And what you're seeing here are it's emission line from typically H alpha in the optical and some other atomic lines that are within our broadband filters. And so we see that very narrow jet coming out of it. In some of the James Webb data, and some of it is what I showed, but too briefly, and some others are other programs, that jet actually is accompanied by slightly more open outflows in different tracers. Like CO is further out than H2, that is further out than the atomic jet. There's a whole temperature and density range around that. But it's connected to the accretion ejection process around young stars.
It's very complicated physics, so I.
Yeah.
Yeah.
And it
I don't touch it, I just observe it, that's all I know.
That's runs over because it marks your.
You know the symmetry axis. In fact, one thing it does tell you, the jet, that's a good point, is that we do know from the jets that the jets are perpendicular to the disks. Which might seem at first like, duh, of course.
Or you get an extra
But people keep talking about warps everywhere in disk between the inner and the outer disk. If that was true all the time, we would find things like this, and we don't.
Yeah.
Like the maximum offset we have is maybe a couple degrees. It's really small.
Then you get an extra axis, right?
Yeah, exactly.
All right, I think the last question goes. I have to decide. To Zirk.
Thank you. I promise it's going to be a quite general question. So when you say you identify a dichotomy in your edge-on disk populations, right? Some are flat, some are sort of flared.
Yeah.
And it's really obvious. What sort of strikes me is that actually you could invert the argument, right? So if you look at disks that are not edge-on, you would expect many of them to be this sort of very flat disk, but there would also be some flared ones.
Yeah.
And we do have observations now where we have inclined disks that are not edge-on, where we actually see some of the vertical structure of the gas.
Mm-hmm.
Do you know, is that dichotomy repeated there?
Okay. That's a great question. I don't have the specific answer because I thought about it at some point and I kind of let it go. But my general thought before going back to the actual papers to answer properly is that the answer is probably no. And the reason for that is I think those flat disks, when you incline them, they will be much, much fainter than the one that are flared. The flared one, the thicker flared ones are just more amenable to the light getting to every single point in the surface of the disk and then to the observer. And I'm guessing a lot of these images from SPHERE, for instance, or other instruments that observe protoplanetary are biased towards the thick flared ones.
Definitely.
And the fact that there's many disks in SPHERE that you don't see or barely see just the inner regions, maybe they're just small, because there's a lot of small disks, that's what ALMA tells us, but maybe they're also just not illuminated outwards.
All right, so I invite everybody who has maybe an additional question to come forward. He's here. Actually, Gaspard is also here the whole rest of the day, so you can find us in the Mercury room. And otherwise, yeah, let's thank the speaker again.